linear transformation is a function, and functions are mappings, and for a linear transformation we will be mapping vectors in one dimension to vectors in another dimension. And the size of the dimensions do not matter. You could be mapping from R3 to R3, or you could be mapping from R2 to R5, or you could be mapping from R7 to R3. The dimensions can be the same or they don't have to be the same. But for it to be a linear transformation, we have these other criteria that must hold true. Graphically, if you graph anything that's a straight line with a linear transformation, it will stay a straight line. It might not be the same straight line, so the slope might be different, but it will not become curved. So straight lines will not become curved. Also, the origin stays fixed. The origin is not going to move. So your function maps 0 to 0. And if it's a linear transformation and you did map the grid lines, so picture taking graph paper and you're going to map all of the points that make up the grid lines on the graph paper, their new image, those grid lines will be parallel and evenly spaced. They might not be perpendicular and they might be spaced farther apart or closer apart, but they will be evenly spaced and they will be parallel to each other. So algebraically, what we were saying is that the transformation applied to a sum of vectors will equal the individual transformation. So T of u plus v needs to equal T of u added to T of v. So I can individually transform two vectors and add, or I could add the vectors ahead of time and then transform them. I should get the same thing. T of 0 equals 0. And if I multiply a vector by a scalar, I should be able to do that ahead of time and then apply the transformation, or apply the transformation to the vector and then multiply by that same scalar. So T of c times u should equal c times T of u. And if you combine the first criteria and the third criteria that we have written here, you could also say that T of c times u plus d times v should equal c times T of u plus d times T of v. An example linear transformation from vectors in R2 to other vectors in R2 is a rotation. Here we have a counterclockwise rotation of 75 degrees. You can see that the line going from the origin to the tip of the beak of the cardinal is 68 degrees. That point, by the way, on the tip of the beak is x coordinate 13.5, y coordinate 33.5. After we apply the transformation, that point on the beak is now at an x coordinate of negative 28.86 and y of 21.71. Notice the origin stayed fixed. So far we can identify that it satisfies that criteria of a linear transformation. Rotations in the second dimension can be accomplished by multiplying by the given matrix. We've plugged 75 degrees in because we're rotating counterclockwise 75 degrees. But the first column will be cosine of 75 degrees, sine of 75 degrees, and the second column will be negative sine of 75 degrees, cosine of 75 degrees. And again, you can substitute that angle for any angle, and you will accomplish a rotation of that degree counterclockwise from the positive x-axis. Continuing to look at our 75-degree counterclockwise rotation, we can see that it preserves vector addition. I'm going to use the point we had previously where we mapped 13.5, 33.5 to negative 28.86, 21.71. And then another point that's in the image of the cardinal is the point x20, y40. Applying the transformation, that point gets shifted to negative 33.46 for x, 29.67 for y. Now, if I added those two coordinates together, so 13.5 gets added to 20, so I added the two x's, I get 33.5. And then if I add the two y's, 33.5 added to 40 gives me 73.5. And I apply the transformation to the sum of those coordinates, I will get negative 62.32 for x and 51.38 for y. Look back at the images of the two original points, and if you add negative 28.86 to negative 33.46, you obtain negative 62.32. And if you add 21.71 to 29.67, you get 51.38. So by looking at a couple of points, we can see that preserving vector addition is satisfied. T of u plus v is equal to T of u added to T of v. Now let's see if our 75-degree counterclockwise rotation preserves scalar multiplication. I'm going to use my same point, x 13.5, y 33.5. It's the point on the tip of the bird. And again, its coordinates after the transformation is negative 28.86 for x, 21.71 for y. If I multiply 13.5 and 33.5 by 3, I get 40.5 for x and 100.5 for y. Now I apply the transformation to 3 times my original point. And my new coordinates are negative 86.59 for x and 65.13 for y. Again, I'm taking cosine of 75 degrees times the x minus sine of 75 degrees times the y. That gives me the new x. Sine of 75 degrees times the x plus cosine of 75 degrees times the y gives me the new y. I'm just doing vector multiplication with that matrix. And if you double check the arithmetic, we see here that negative 86.59 for x and 65.13 for y is equal to 3 times negative 28.86 and 3 times 21.71. So if I apply the transformation to 3 times my vector, it's equivalent to 3 times the transformation of the original vector. So T of C times U is equal to C times T of U. Notice that the line that connected 0 to the tip of the beak of the bird stayed straight. It did not become curved. So notice we're preserving linear shapes. The line stayed straight. It did not become curved. Another example of a linear transformation from R2 to R2 will be a reflection about the x-axis. That is, the image gets flipped upside down across the x-axis. It can be accomplished by matrix multiplication with the matrix that has first column 1, 0 and second column 0, negative 1. Now notice when I plug in the origin 0, 0 and I go through the matrix multiplication, I will still get 0, 0, and we can see from our image in which we applied this transformation to every one of those points in the cardinal, and notice the origin stays fixed. It stays, at the tip of that segment at 0, 0. Applying the transformation to a couple of different points, notice when I apply it to the point that's at the tip of the beak of the cardinal bird, x is 13.5, y is 33.5, 1 times 13.5 added to 0 times 33.5 is going to give me 13.5 again for the x. So the x stays the same, but 0 times 13.5 plus negative 1 times 33.5 is going to give me the opposite y. So the y got flipped to be the opposite, and the image gets flipped upside down. You could see that also occurred with our other point. Looking at the graph, we didn't apply the transformation to the grid lines, but if we did apply the transformation to the grid lines, they would, in this case, they would kind of look the same because they would just flip upside down, but they would stay parallel and evenly spaced. In the previous transformation where we rotated, if you pictured all the grid lines just rotating 75 degrees, you could picture that they would stay parallel and evenly spaced. Reflections about the x-axis do preserve vector addition and scalar multiplication. Here I have added those two original points together to get 33.5 for x and 73.5 for y. When I apply the transformation, I get 33.5 for x and negative 73.5 for y, and that's equal to adding those two other transformation points together, the two image points. So 13.5, negative 33.5 added to 20, negative 40 gives me that same point. So T of u plus v is the same as T of u plus T of v. And if I multiplied one of the points, I just picked the 2040 by 2. So 2040 became 4080. And I apply the transformation to get 40 negative 80. That's the same as 2 times 20 negative 40. And 20 negative 40 was the image that we got when we applied it to 2040 in the first place. So scalar multiplication is preserved. T of c times u is the same as c times T of u. Now we have been describing some examples of linear transformations by matrix multiplication, and that will always be the case. If you have a linear transformation that satisfies all of the criteria that we've pointed out and fits the definition of a linear transformation, there will always be a unique matrix A such that the matrix multiplication by that matrix A gives you all of your new images. And we will use the notation T of x equals A of x. If you see that notation, it's referring to a linear transformation, mapping vectors in one space to vectors in another space with matrix multiplication by matrix A. In R2, it's important to point out that given matrix A that represents a linear transformation, the first column tells you where the unit vector I is mapped, and the second column tells you where the unit vector J is mapped. So in R2, I refers to the standard unit vector 1, 0, J refers to the standard unit vector 0, 1. And in a linear transformation, the first column tells you where I is mapped with this transformation, and the second column tells you where J is mapped with this transformation. So notice if I plug 1, 0 into this transformation, I will obtain negative 4 times 1 plus 1 times 0, or negative 4 for the new x. 2 times 1 plus 6 times 0 equals 2 for the new y. If I plug 0, 1, or j in, I will get negative 4 times 0 plus 1 times 1, or 1 for the new x, and 2 times 0 plus 6 times 1 equals 6 for the new y. So I got mapped to negative 4, 2, and j got mapped to 1, 6. And then in general, you can accomplish the transformation by going through the matrix multiplication with any point that you have. So any new x will be negative 4 times x plus 1 times y. The new y will be 2 times x plus 6 times y. The idea of the columns in your matrix A that defines your linear transformation, mapping the unit vectors stays true for all dimensions. So in R3, I is 1, 0, 0. J is 0, 1, 0, and we have a third standard unit vector K, 0, 0, 1. And for a linear transformation from R3 to R3, the first column tells you where I gets mapped, the second column tells you where J gets mapped, and the third column tells you where K gets mapped. So notice I've plugged J into this example, and 8 times 0 is 0, plus 5 times 1 is 5, plus 9 times 0 is 0. So add those, you get 5. And then 6 times 0 plus 3 times 1 plus 1 times 0, you get 3. 7 times 0 plus 0 times 1 plus 1 times 0, you get 0. So J got mapped to 5, 3, 0. And I can plug any point in R3 in. I've plugged the random point, 0.8, negative 0.3, negative 1. So that's a vector that's represented by that terminal point, 0.8, negative 0.3, negative 1. And if I apply the linear transformation to it, I'm multiplying across the row of the matrix A and then down the column vector. I will get a new X location of negative 4.1. I'm dotting across the middle row down the column vector. A new Y location will be 2.9. I'm dotting across the third row and down the column vector, and I get a new Z location of 1.9. So that is a way to picture linear transformations. You're taking points and you're shifting them in space. And if you're in R2, the first column tells you where the vector down the x-axis goes. The second column tells you where the unit vector on the y-axis goes. If you're in R3, the first column tells you where the unit vector down x goes. The second column tells you where the unit vector in the y direction goes, and the third column tells you where the unit vector in the z direction goes. Now this idea again is expanded to higher dimensions. In general, the unit vectors in higher dimensions are not called I, J, and K anymore, because you could have any number of, vectors depending on how high your dimension goes. So instead, they'll use notation E sub 1, E sub 2, E sub 3, E sub 4, and they're referring to the unit vectors. 1 would be the x direction, 2 would be the y direction, 3 would be the z direction, etc. When a linear transformation is a function mapping one set of vectors in Rn to another set of vectors in Rm, Rn, what you're mapping from, is the domain, and Rm, the space you're mapping into, is called the codomain. When you take a vector in Rn and you apply the transformation and you get the new vector, it is called the image of x for that linear transformation, and the set of all possible images created by a certain transformation is called the range of the transformation. So with our example that we saw earlier, again, you're accomplishing the mapping by doing matrix multiplication of this 3 by 3 matrix. And so the image of any vector will be given by the arithmetic 8 times x plus 5 times y plus 9 times z for the image x, 6 times x plus 3 times y plus 1 times z for the new image y, and 7 times x plus 1 times z for the new image z. In this case, the domain is R3, the codomain is also R3, and the range is all of R3. This particular transformation can map to any vector in R3. There is no vector in R3 that cannot be reached by applying some vector into this linear transformation. So in this case, the codomain, what I'm mapping into, equals the actual range. But the range might be a proper subset of the codomain. You might not map to entire all of R3 or entire all of R2 or entire all of R4, whatever your codomain is. The range might be just a subset. This example, in which our matrix multiplication is being accomplished by the matrix that has first column 2, 1, 4, second column 1, negative 4, negative 7, and third column negative 3, 1, negative 1, we map vectors in R3 to a plane in R3. So the range is this plane in R3. The domain is R3 because I'm mapping vectors from the third dimension. The codomain is R3 because I'm mapping two vectors in the third dimension. But the range, the set of all possible images, is not all of R3. Instead, it's just this plane. If you did RREF, the original matrix A, you will see that you have two pivot columns, showing that matrix A is a two-dimensional space in R3. And we have an image of that shown here as the plane. Another example showing that your range might not be the full codomain. If we took the 2 by 2 linear transformation with first column 2, 3 and second column 6, 9, and we applied it to any point in R2, so if we applied it to any of these points on the cardinal bird, they get collapsed to a line. Every point on that cardinal bird is mapped to a point on the line y equals negative x over 3. So you had a two-dimensional space collapsing to a one-dimensional space. So the range is just all the points on that line. It looks like a segment here because I only mapped the points on that cardinal bird. But if you picked other points in R2, you could plug them into this transformation and they would form other points on that line. So the domain, what I'm mapping from is R2. The codomain, what I'm mapping into is R2, but the range, what I'm actually mapping is this line in R2. A linear transformation is onto if the range equals the full codomain. And a linear transformation is one-to-one if in the range each vector has been mapped by only one vector in the domain. So any vector in the codomain for a one-to-one transformation has either 0 vectors mapped to it or 1 vector mapped to it. You can have a one-to-one transformation that's not onto. Okay, our example in which we were using the 3 by 3 matrix 8, 6, 7, 5, 3, 0, 9, 1, 1, that transformation happens to be one-to-one and onto. We map to the full set of R3 and it's one-to-one. Every image was obtained only by one vector that was plugged into the transformation. Our example where we collapse the cardinal bird onto the line, that transformation is not onto, nor is it one-to-one. There are points on that line that can be obtained by more than one vector being plugged into the transformation, and we obviously are not covering all of R2, we're only covering that line. The RREF of the matrix A can tell you a lot about whether or not a transformation is one-to-one or onto. When we RREF'd our 3 by 3, we get the identity matrix showing us that all three of those vectors that we're mapping I, J, and K, they are independent. They are linearly independent. And so they point in 3 different directions, and thus you can create linear combinations that span all of R3. So it is onto, and it is also one-to-one. Any vector I'm trying to map to is only going to have one solution. So by RREFing the matrix A, I get the identity matrix that tells me that my transformation is one-to-one and onto. Now when I RREF'd the transformation that collapsed the cardinal bird to the line, I get 1, 0, 3, 0 as the RREF'd matrix, and that's one describing the line that we map to. It's also showing me that it's not onto and it's not one-to-one. By the way, transformation matrices do not need to be square. We were looking at a lot of examples in R2 and R3 that were square, but they don't have to be square. Here we have a matrix A that is 3 by 7. And we will plug in matrices in R7 in order to accomplish that matrix multiplication. So notice 3 by 7 must multiply 7 by 1, and we will get a result that is in R3, 3 by 1. So my domain is R7, the 7th dimension. My codomain is R3, the 3rd dimension. When we do RREF this matrix, we will see that there are 3 pivot columns. That means there are 3 independent vectors. Thus, this matrix does give us a transformation that is onto. Because we have 3 independent vectors, we can span all of R3. So this transformation is onto. But all 7 vectors are not independent, and so this transformation is not one-to-one. We will be able to find different 7 by 1 vectors, apply this transformation, and get the same output in R3. So it is not one-to-one. Another example of a non-square linear transformation, I have A as a 5 by 4 matrix. I will plug in vectors in R4 so that 5 by 4 can multiply 4 by 1. I get out 5 by 1 vectors. So my domain, what I'm plugging in is R4, the 4th dimension. My codomain, what I'm getting out, is R5, the 5th dimension. When we RREF this particular matrix, we would see that there are 4 pivot columns, showing that there are 4 independent vectors. So this matrix is not onto, because 4 vectors cannot span all of the 5th dimension. So it is not onto. But all 4 vectors are independent, and so this transformation actually is one-to-one. To get any vector in R5, there's only going to be one vector in R4 that will map to it. So again, it's not onto, but the space that it actually maps in R5 is a one-to-one space. So again, you're mapping to a subset of R5. Every vector in that subset has only one vector from R4 being mapped to it. So it's not onto, but it is one-to-one. If you do have a square linear transformation and it is one-to-one, then the following statements are all true. But again, this is applying to the assumption that you are dealing with a square linear transformation. So if your matrix A is accomplishing a one-to-one linear transformation, A will be invertible. It will be row equivalent to the identity matrix. Thus, it will have n pivot columns. Thus, the homogeneous equation AX equals 0 will have only the trivial solution. The columns of A will form a linearly independent set. All the columns will be linearly independent because it RREF to the identity matrix. And the fact that A has an inverse means that there is a transformation such that you can undo matrix A transformation. So S of T would equal T of S will give you back your original vector that you plugged in. So linear transformations have inverse transformations if your matrix A is invertible. You'll be able to undo the transformation with another matrix like you do with inverse functions in regular algebra. The equation AX equals B will have only one solution for any B in the codomain. And the columns of A will span all of the codomain. So every vector in Rn can be written as a linear combination of the vectors in A. That's what spanning Rn means. Every vector in Rn can be written as a linear combination of the vectors in your matrix. And the next two statements are basically just repeating what we said a little bit earlier, that there will be an inverse matrix such that C times matrix A gives you the identity matrix, and A times that matrix will give you the identity matrix. So C and D will be the same matrix. It's just pointing out that you'll be able to multiply either side by A and get the identity matrix. Remember that definition of rank? Rank means that it's the full space that A spans, and so the rank of matrix A will be n. And then the null space, remember the null space is the solution set when your equation set equal to 0, contains only the 0 vector. If A is not invertible, meaning if A does not have an inverse, then none of those statements are true. Now, the more you study linear algebra, the more some of that list just seems completely repetitive, because you'll realize that all of these statements are just different ways to say the same thing. So if you're already feeling that way, that means that you're absorbing a lot of linear algebra. But, you know, at the beginning, they all are kind of separate statements, but in the end, they are statements that do indicate the same thing. So if A has an inverse, it will represent a one-to-one and onto linear transformation, and it will REF to the identity matrix. It will have n pivot columns, so its rank will be n. Any equation has only one solution, so setting the equation equal to 0 is only going to have 0 as the solution, etc. There is a set of useful transformations in R2, and R3 has a similar set, but we're really only going to highlight the ones in R2. And we've already talked about rotations, so if you rotate counterclockwise from the positive x-axis, then the matrix shown here with first column cosine theta, sine theta, second column negative sine theta, cosine theta, it will accomplish that counterclockwise rotation. A reflection through or about the y-axis is given by first column negative 1, 0, second column 0, 1. So it will reflect across the y-axis, so it'll flip it sideways. We already looked at a reflection about or through the x-axis where we flip the image upside down. That was given by first column 1, 0, second column 0, negative 1. A few other useful transformations. One is a reflection through the line x equals y, and that's accomplished by first column 0, 1, second column 1, 0. You can also reflect across the line x equals negative y, and that would be accomplished with first column 0, negative 1, second column negative 1, 0. And a reflection about the origin, which means you flip across the y-axis and you flip across the x-axis, you flip across both, is accomplished by first column negative 1, 0 and second column 0, negative 1. Now, it is helpful to look through this list and kind of memorize these matrices, but if you plug any point in, you can realize what the transformation does. So I wouldn't worry so much about memorizing. Instead, put an example point in and see what it does. So for example, the third one we just talked about, reflection about the origin, if I put in xy, I will get negative 1 times x plus 0 times y, so I'll get negative x, and then I'll get 0 times x plus negative 1 times y, I'll get negative y. So my image will be negative x, negative y. That's the same as flipping about the y-axis and then flipping about the x-axis. So I don't really have that memorized, I just quickly plug a point in and see what I obtain. Besides flipping images and turning images, we can also skew images, and squash them or stretch them out. So horizontal contractions or expansions, meaning I'm stretching or squashing horizontally, is accomplished by first column some constant and then 0, and then second column 0, 1. And that will stretch or squash my image horizontally. If k is less than 1, it'll be a contraction. If k is bigger than 1, it'll be a stretching or an expansion. For vertical contraction or expansion, first column is 1, 0, second column is 0k. Again, if k is less than 1, then you're squashing or contracting. If k is bigger than 1, you're stretching or expanding. A vertical shear is accomplished by 1k for the first column, 0, 1 for the second column, and a horizontal shear is accomplished by 1, 0 for the first column and k1 for the second column. Here we have shown a horizontal shear where the k was 0.75. So we multiplied by 1, 0, 0.751. And you could see the cardinal bird gets kind of shifted and stretched diagonally. That's what's meant by a shear. Again, you want to read over the list so you're very familiar, but I wouldn't worry so much about memorizing the list. Instead, plug in some example points and see what the transformation does to that point, and you can kind of realize, whether it's a reflection or a contraction or an expansion or a shear or a rotation, etc. An example we actually saw earlier in chapter 1 about 3D rotations, those matrix multiplications are also linear transformations. So we were actually been working with linear transformations a little bit throughout our study of chapter 1. So for linear transformations, you want to know the algebra and the graphical criteria about the origin staying fixed, lines remaining straight, grid lines remaining parallel and evenly spaced, vector addition being preserved, scalar multiplication being preserved. You also want to understand how you can map R3 to R3, or you can map a bigger space to a smaller space, or a smaller space to a bigger space. The RREF of the matrix A tells you a lot about where you're mapping and whether your transformation is onto or one-to-one. Also, the matrix A tells you where the unit vectors are mapped. So the first column tells you where I is mapped, the second column tells you where J is mapped, the third column tells you where K is mapped if you're working in R3. And then in R2, there are some common useful transformations, and so you want to be familiar with that list. Again, you'll find dealing with that list easier if you realize you can just plug in an example point and kind of see what it does to that point.